record this a little bit. Okay, so molecular representations. So I often call this the chemistry hieroglyphics. Now, and there's lots of ways that chemists have developed on how to draw molecules. And each sort of method has got its own advantages and disadvantages. And so I thought I'd go through them and talk about the one we're going to use the most. So the one which is probably the most familiar is our Lewis structure. So each line represents a bond which contains 2 electrons. Each atom is explicitly drawn carbon, which is bonded to 3 hydrogens and another carbon. Carbon, which is bonded to an oxygen. And you draw the lone pairs on the oxygen, so you know that oxygen's got some lone pairs. So the advantage of drawing a Lewis structure is that basically every single bond is explicitly drawn and you know exactly what everything is connected to. The main disadvantage to Lewis structures and why we've come up with other ways of drawing stuff is that this is time consuming and it takes up a lot of space. So this molecule takes up a lot of space, and particularly when we get into more complex molecules, drawing Lewis structures just becomes too much work. Then there's the partially condensed structure. So all of these molecules are exactly the same here, where we're not explicitly drawing the carbon bonded to the 3H. We just put H3 here, and which signifies that this carbon's bonded to those H's. So there's, and notice how I drew the H first and not CH3 and then the bond, because sometimes you can get into some connectivity issues here. This partially condensed structure certainly saves some time, but it's still time consuming to draw, and things can get confusing with the connectivity of the atoms. So this is used often in, like if you're in sort of journals and that sort of stuff. It was particularly used like a long time ago in old journals, very often. Let me move some of the stuff so I can see what's going on here. Then we had condensed structures, which were quite, in some ways, quite problematic. So the advantage of a condensed structure is that you don't need any special drawing program to draw it. You can use a keyboard, but the connectivity definitely becomes an issue unless you think about this really, really carefully. So two CH3s are connected to this carbon, which is connected to an H. And this carbon is bonded to this oxygen, not this hydrogen. Yeah, so the big advantage is you lose sight of the connectivity. But the advantage is you can just write it into you can just type it in. Now, the structures that are the most commonly used now are what we call these line bond or skeletal structures. And so here you'll notice a couple of things immediately. It's just a series of lines. We still see the oxygen and we see a little proton attached to the oxygen, but all of the protons attached to the carbons are gone, and the carbons themselves aren't explicitly drawn. So the big advantage is it's quick. As you get used to it, it's easy to read, and they're really simple to draw. Let me move this up to the top. So this is where we're going to be working from: line bond structures or skeletal structures, and being able to convert a Lewis structure to this is quite important. Now, there's certain rules here. So the lines are basically representing bonds. And so where these lines here intersect, that is a carbon atom, which would represent that carbon atom there. And at the end of this line, this represents a carbon atom, which would be one of these CH3s. This would be the other CH3. And then the protons, we don't bother drawing them because we know that carbon's got a valency of 4. So if we only see one bond to carbon, that means that mentally we just say we know that that carbon's bonded to 3 hydrogens. Likewise, this carbon here is bonded to a carbon there, carbon here, and oxygen. So it's got 3 bonds. So that means the 4th bond, it has to be bonded to a hydrogen. So that's basically the way it works. So there's here's some examples of a Lewis structure and then a line bond structure or skeletal structure. Our favorite molecule in the morning, caffeine. So it takes a while to draw this beautiful molecule out. And so the line bond structure, this carbon would represent this carbon here. It's bonded to a nitrogen. So you draw that. So one of the things you'll notice is that every atom that isn't a carbon or a hydrogen, you draw out. You draw out the oxygens, you draw out the nitrogens. If there was a sulfur there, you draw out the sulfur. Any heteroatom, you draw out. Anytime a hydrogen is attached to a heteroatom like oxygen here, you draw it out. So you have to draw out hydrogens only if they're bonded to heteroatoms. If it's bonded to a hydrogen, to a carbon, you usually just leave it out. So carbon atom double bonded to carbon. So carbon double bonded to carbon, carbon bonded to carbon, carbon bonded to carbon, carbon double bonded to this oxygen here. So they're very elegant structures. It's always good. Some textbooks, or I shouldn't say some textbooks, certainly some older textbooks never used to draw the lone pairs on the heteroatoms because the word processing that they were using was complicated and putting them there was time consuming. So they never used to do it. They just used to, students were just had to assume that oxygen's got a octet, complete octet. So if it's got 4 electrons here, there must be 4 electrons here. But with today's sort of modern word processing and graphics, now lone pairs are drawn everywhere. And it's always a good practice to draw the lone pairs in your molecule. So the rules are really simple. Carbon atoms are not shown. We assume carbon atoms are there at the intersection of lines or at the end of lines. So in the first example, at the end of this bond, we assume a carbon atom's there. At the end of this bond, we assume there's a carbon atom there. Here, a bunch of bonds are coming together, carbon atom is there. So rule 1, you don't draw carbon. Perfect. Rule 2, you don't draw hydrogen unless it's bonded to a heteroatom of some type. So if it's bonded to carbon, you don't draw it. So you don't need to draw carbon atoms because you draw the bonds that the carbon atom is when it's bonded to another carbon or a heteroatom. And then you don't draw the hydrogen. So this carbon here, it's at the end of a line, there'd be a carbon atom there. You notice it's bonded to 1, 2, 3 hydrogens plus this nitrogen. So this carbon, we know it's bonded to nitrogen, so that's 1 bond, and it's got a valency of 4. So that means that this has got 3 hydrogens attached to it. Here we'd have 3 hydrogens, here we'd have 3 hydrogens. This carbon here, it's got 1, 2, 3 bonds to nitrogen, so that means that there's 1 left, so that would be the hydrogen, which is there. Takes a little while to get used to, but when you, in the end, it becomes quite second nature, I suppose. This carbon here, it's got 1, 2, 3, 4 bonds. Its valency is 4, so there's no hydrogens here. Likewise with this carbon, 1, 2, 3, 4, so there'd be no hydrogens, And the third rule is atoms other than carbon and hydrogen are shown. And so we include the lone pairs on that. So the nitrogens were shown, the oxygens were shown, sulfur would be shown. And so here are some more examples of this. So drawing this 6-membered ring here, and then adding all these hydrogens, you see they take up an awful lot of space. And so this is a much cleaner, simpler structure. But this carbon here, it's got 1 bond, 2 bonds to carbon. So it's missing 2 bonds. So we would say it's got 2 hydrogens. Likewise, this would have 2 hydrogens. This carbon here has got 1, 2, 3 bonds. So it's only got 1 bond to hydrogen. So second molecule, we got sulfur with so bonded to H. We have to draw this H because it's not bonded to a carbon atom. Bromine over here, draw the lone pairs, draw the lone pairs. And this is another 6-membered ring with some double bonds. We have to draw the OH. Here, a CH3. This carbon's bonded to that carbon, so it's got 3 bonds left, all the hydrogens. We just don't draw them. And there's the 3 hydrogens there. Okay.